Hello everybody, welcome back to the Gregorius Maths video. In this video we're going to be pressing on with algebra, pressing towards Galois theory and even further some stuff about homological algebra, pressing on with algebra basically, and we're going to be looking at polynomial rings. So I'm assuming that we're all familiar with polynomials, but now we're going to look at them with coefficients, not just in the real numbers or complex numbers, but with coefficients in general ring R. And this is denoted R of x. And this is defined as the set of all an x to the n plus up until a0, such that all of these ai are in some ring R. Now, where R is, I'm just going to write that R is a ring. Alright, now, it actually turns out that this is actually a ring, so the polynomial ring is a ring. Now, addition is defined as, so, if we let f and g be polynomials with coefficients in this ring R, then we have that f plus g, and I'll just specify that f is equal to a n x to the n plus up until a0, and g is equal to a m x to the bm x to the m plus b0. Alright, now, and if we want to write this a bit more concisely, we can write this as the sum over ai x to the I, and this is equal to the sum of bj x to the j. Alright, there we go. Now, we can define f plus g as being, now I'm going to assume that n is bigger than or equal to m, right? So this is equal to an plus bn x to the n plus an minus 1 plus bn minus 1 x to the n minus 1 plus up until a0 plus b0. And I'm just gonna write this out as a summation, nice summation. This is equal to the sum of ai plus bi x to the I. And it's assumed that, so clearly I've assumed that this degree of f is bigger than or equal to the degree of g, which I'm allowed to do because otherwise what would happen? The degree of g is bigger, then I just replace all the n's with m's and the same thing holds. So that's perfectly reasonable. So I'll just write that n is bigger than or equal to m, and bi is equal to 0 whenever I is bigger than m. So all of these bn's, so when we're between bn and bm plus 1, that's all going to be 0. Alright, so addition is pretty simple, to be honest. Now, multiplication is a tad more interesting. Fg, this is equal to c m plus n x to the m plus n plus c m plus n minus 1 x to the m plus n minus 1 plus up until c0. And we can write this out as the sum over ci x to the I. But what are these ci's? Well, this is just the sum over I of the sum over j of aj b I minus j x to the I. So this summation right here, this just shows us what the ci are precisely. So, but it's just neater to write them out like this. So an important observation is that the degree of fg is equal to the sum of the degrees of this. And so that's going to be the first thing that we show. Actually, if R is a commutative ring, then the polynomial ring will also be commutative. But anyhow, let's push forward with another theorem. A first theorem. So theorem. Now, the first one is fairly obvious, so I'm just going to denote the degree by D. So, if R is a ring, and F and G are in the polynomial ring with coefficients in R, then the degree of FG is equal to the degree of F plus the degree of G. Now this one's quite easy, but the nice fact, the further fact we can show is if R is an integral domain, so I'll just write ID for short. If R is an integral domain, then R of X is 2. Now this one is the more interesting one, so let's prove this. So let's just assume that Fg equals 0 for some polynomials in this ring, then that implies that the degree of Fg equal to the degree of F plus the degree of G is equal to 0. If Fg is equal to 0, then this right here means that F and G are both constant polynomials, which means that F and G are in R, but since R is an integral domain, this implies that F or G equals 0. There we go. Alright, so let's keep going. There's another interesting theorem about the units of this polynomial ring. So the theorem is, if R is an integral domain, the units of R are precisely the units in R of X. Sorry, all of these pens are running out. I'm just gonna grab it. Fresh packet. No, it's not that. Do excuse me. Do skip this part of the video if you wish. Aha, here we go. Fresh pens, let's go. Alright. I'm just gonna lay them out on the bed for now. Alright, we'll carry on with blue, I guess. Alright, so the proof. Oh, that's nice. Fresh pens smell alright. Alright. Alright, so the proof is, so one way is clear, so, apologies, the units in R are obviously going to be the units in R of X, right? But the other way around, the units of R of X being the units of R is not so simple. So let's just see, let's assume Fg equals 1, where F and G are both polynomials with coefficients in R, then because R of X is an integral domain, F and G are not equal to 0. Now, the degree of Fg is equal to the degree of F plus the degree of G, which is equal to 0 because the degree of this is just going to be 0. And now, this means, because this means that the degree of f and the degree of g are equal to 0, which implies that f and g are in R, because they're constant polynomials, which means that they are units in R, since f times g is equal to 1. So that's a nice fact about the units of the polynomial ring. So yeah, now we'll move on to things with more than one variables. So we'll have a definition. R of x, y is defined as being the set of formal sums over I and j of a, I, j, x to the I, y to the j. Alright? Now, clearly there's some interesting things about this too. So the first thing to note is, let me just write this y to the j a bit clearer. So the first thing to note is obviously that there's two variables. So an example might be x squared plus y squared minus 1, for example, and this would have a degree of 2. Now, the degree of this is just going to be the highest one. So, for example, the degree of this one, where y is 5 now, the degree of this is just going to be 5. Okay? Alright, so let's see. So there's one theorem about these which I would like. Actually, there's two theorems about these which I'd like to prove. So one of them is going to be really similar to this one, and one of them is going to be quite a cool theorem, which one may suspect. I'm not sure. Alright, so the first one is, if S is equal to R of X, then R of XY is isomorphic to S of Y. And I'm not gonna give a proper proof. I'm just gonna give an example of this. So, illuminating example. Alright, so the illuminating example is, well, let's just take a look at Q. So the rationals of x and y, and let's have f equal to 2/3 x squared plus, 5y to the 5th minus 1 be one of these. Then what we can do is we can use a nice argument here, and actually let's just stick in so x squared y. We'll just do that, something like this, and we'll just have we'll just have 5x y squared. I don't know. All right, now the trick here is we just consider these x's as coefficients. So this is going to be equal to 2/3 x squared y plus 5x y to the 5th minus 1. And now this is just going to be in, well, the coefficients are going to be in Q of x, so it's just going to be like this right here. And similarly, we can use a similar argument to show that f is also in q of y, x. And hopefully this is illuminating, so it gives you an idea of how to prove this, because s of y is just going to be r of x of y. So it's going to be something like this. And that's a interesting theorem, I think. And this, I really like this type of example. Alright, so one more thing about these polynomials with kind of more than one coefficient. Polynomials? No, that's not what they're called. I don't know what they're called, but whatever. And that is a similar one to if we take a look at this one, sorry, no, not this one, of course I rubbed it out, the one which says that if R is a integral domain, then its polynomial ring R of X is also going to be an integral domain. Well, guess what, chaps? That's going to hold for n variables. So if R is an integral domain, then R of x1 da la la xn is an integral domain. And the proof of this is clever. The proof of this is clever. What you do is, I'm just going to show, well, yeah, I'm not going to do the full proof, but I'm just going to show it for two variables, and again, kinda, I'll put kinda in brackets. So we're just going to have R of x, y, and this is isomorphic to R of x of y, and since R is an integral domain, this right here is an integral domain, and so by the original theorem that the polynomial ring of an integral domain, well, this right here is just the polynomial ring of an integral domain, because it's just, this right here is an integral domain, so it's going to be an integral domain of y, and that right there is an integral domain. Yeah, that's literally how you do it. And I'm sure that you can kind of induct on n variables or something like this, but that's how you do it for two variables. And that is a nice proof right there. I really like this proof. It uses a previous theorem and it follows almost immediately. Alright, now there's one more thing to discuss, and that's the evaluation map, and then we'll be done. So, again, I'll leave it to you to show that it's a ring homomorphism. And how is it defined? Well, let's see. Let me put a definition. Let, let's say, yeah, R be a subring of S, then the map phi, let's say, alpha, which takes in a polynomial and it's going to output an element of S. And what's it doing? Well, it's sending a n x to the n plus da la 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 a0. It's sending that to a n alpha to the n alpha plus da la 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 a0. So it's actually just evaluating the polynomial at alpha. So yeah, this is called the evaluation map, called evaluation map at alpha, and this is a ring homomorphism. So ring hom. And I'll leave it to you to check this, but it is indeed a ring homomorphism. And so, yeah, we'll take a look at a couple of examples and see what happens. So, one nice example is, so yeah, from now on just be looking at some examples. So, let's just have phi 0 from q of x to, I don't know, r. Well, what's that going to do? It's just going to send a n x to the n plus da la 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 a0. It's just going to send it to a n 0 to the n plus da la la a0 equal to a0. So it's just going to send any polynomial with coefficients in q to the real number that's at the end of it. So this is what the evaluation map at 0 does. Now there's another example. So we'll have a map, the evaluation map at 3 from, again, q of x to r. And what's this going to do? We're going to look at a specific example, which is sending x squared plus 5x minus 6 is sent to 3. Sorry, at 3. So it's going to send it to 9, 3 squared plus 15 minus 6. And I just realised I meant a plus here. Sorry. I meant a plus here and a minus here. Sorry, my bad, guys. And then we're going to have a minus, plus, and this is equal to 0. So, therefore, the polynomial x squared plus, minus 5x plus 6 is in the kernel of phi 3, the evaluation map at 3. And that's a nice example. So we'll do another example where we have an evaluation map at a complex number, so just at I. And yeah, that should be the final example, I guess. And then I'll close off this quite detailed discussion of polynomial rings, if I do say so myself. So the final example is, yes, we're not limited to the real numbers. Example. Let phi I from q of x to c. Well, what's it going to do? It's going to send a n x to the n plus da la la a0. It's just going to send it to a n I to the n plus a0. And so, an example of something which is in the kernel of this, well, a famous one is x squared plus 1 is in the kernel of phi I from q of x to c. That's a nice example. And one thing I forgot to mention is polynomial rings are really interesting. Some polynomial rings are really interesting. And one of the really interesting examples which I haven't covered at all today is, so I'm just going to put down the pen now, is the polynomial ring with coefficients in the integers modulo n. So for example, modulo 2, that's one of the smallest rings. Now, clearly this ring is going to be infinite, because, you know, you could just let the degree go to infinity. So the polynomial ring, and actually I'm just going to make the notation a bit easier, I'm just going to do it like this. So like this. This clearly has infinite elements, but its characteristic is just 2. So polynomial rings give rise to really interesting examples of fields because they have finite characteristic, but they're infinite fields. So yeah, that's a really interesting example. Anyway, I hope you found this video informative and helpful and enjoyable to watch. And until the next time, I'll see you then, where I will hopefully press on with algebra. Goodbye. Bye bye.